now starts to do
All right. And I haven't run a new sheet because I've had some people switching classes and so forth. And so I will do that over the weekend, or hopefully you get the grades finalized. And so I will be going around and checking homework again next week, starting on Monday probably. So, okay. Because I'm going to be checking homework, or oh, I did. All right. So, and today we're not really going to spend much time going over that parametric stuff because most of those homework problems I think were very similar to what we did in class. If you do have some issues with some of those, be sure and get in to see me. Look them up in here and so forth. Like 17, for example, I think was just kind of a restating of example 10 and the one we worked in class. So you had to answer the question about that. 18 just changed the 150 to a 100 and asked you kind of some of the same stuff. And then 20 gave you the X and Y equations and asked you very much the same questions that we went through when we went through example 10 as well. Where does the ball land? How high is it? What speed's it going? Those kind of things. And so pretty much the same business. So if you've got some issues with those things, be sure and come see me on those. The sample one packet here, as we think about the midterm test coming up, we want to look at some of these multiple choice ones. Anybody have one that they'd like to look at here? Don't everybody speak at once.
They just have to take the midterm
Or,
What?
yeah, geez, yeah, exactly. We must be ready to go.
on
Well, that's one thing it could mean. It could mean we're all ready to go, or
We just don't know.
or the answer could be all of them, or I haven't done any of them, or Robbie.
43.
43. Okay. And like I said yesterday, at some point in time, and I have had a few people already coming in, asking me, about some or checking. Remember, this is the answer book for the sample packet. It's got them worked out. You can check answers. I'm perfectly fine with you doing that. And we are going to hand it in, and I'll be looking at effort points and stuff as well. I prefer you don't come in and just copy down everything for every problem. That doesn't do you really a whole lot of good for the midterm. That's the whole point of this, is to improve your chances on the midterm. So let's look at 43. How many points on this curve will the line tangent to the curve pass through the origin? That's a pretty good one to start with right there. Wow. Yeah, because this one does have a little bit going on in it. You can use a calculator, so you can graph this thing and give you a sense of what's going on. But let me just put kind of just a general kind of a picture. I have no idea if this is even remotely what this looks like. But it doesn't really matter. But the idea is that you would get that there's probably a point right back here where this tangent line would go through the origin, right there, like that. And there might be another one. In the way I drew this picture, that might be about the only tangent line that would go through the origin. But that's what they're asking for. Okay, so Robbie, what'd you try?
I tried graphing it on my calculator, and then
Did you use a derivative at all?
I found it, then I wasn't really sure what to do.
Okay, this I'd kind of forgotten about this question. Usually, most years we get into one like this. Well, I think in your homework today, actually, there's going to be a problem that's going to. So going through this maybe is going to help some of you guys in this particular problem because it has some similarities to a problem we do today. Here's what you would have to do. So let's just graph this thing, and what we're looking for is a point, or a point on this curve where the tangent line crosses the origin. Okay, so this picture would represent what we're talking about. Now, what we don't know is what this point is. So I'm just going to call that point XY. Okay, just for some random point that we don't know where it is, it would have coordinates XY. Now, I happen, though, to know what Y is. What is Y? Not an actual number, but I know what Y is. What is Y?
That
That right there is y. So I could replace the y here. I could call that point x, and then 4x to the 5th minus 3x to the 4th, right? I could call that point that right there instead of x comma y, right? I can call it x and then comma and then that. All right? So now, what do I know about this dotted line right here? Well, I know that it has a slope where I could subtract, I could do a slope formula on these 2 points right here. Would you agree with that? Now it's going to have x's in it, but I could do this. I could do 4x to the 5th minus 3x to the 4th plus 15x squared plus 6 minus 0 all over. So that is, I subtracted the y. So I subtract this y, subtract that y, right? And now I'm going to take this x and subtract this x, right? And that is the slope of that line. Would you buy that? Okay? It's just 2 points, slope form. There's another way we could write the slope of that line. What is something we have learned that is the slope of the tangent line? The derivative. Very good. The derivative of a function is the slope of the tangent line. So the slope of this dotted line is this, but it's also the derivative of this. So I can set this equal to the derivative of this. Now we have not had a situation to use this in this idea in the past, but we will again in the future. 2 different ways of writing the derivative, or excuse me, 2 different ways of writing the slope of this tangent line. The slope of the line could be done with 2 points. Now here's the thing. In a lot of our derivative problems, the reason this hasn't come up yet, is in a lot of our derivative problems, do we know 2 points on the tangent line? How many do we know? 1, just where it touches the curve, right? That's the whole point. It's a tangent line. It touches the curve at 1 point. We only know 1 point. So we learn the derivative is that slope. But in this problem, we actually know that the tangent line crosses at another point. So we know 2 points. So we now know 2 different ways to write the slope. One is the derivative, one is the slope between 2 points. And now we can just get on our calculator and solve that equation. So let's do that. So let's just, of course these zeros don't matter on this one. Okay, so get on your calculator and do a solve. This equals that. Now we're going to do a problem in your homework today that I call the Shanghai problem. You'll understand when you read it. We'll do another problem in reviewing our parametric equations next week that I call the Luke Skywalker problem. Both of those have this idea where we can draw a picture and we can set up 2 ways to do slope. One is slope between 2 points, one is derivative, and we can set those equal to each other because they're the slope of the same line. So often throughout the rest of the year, I'll refer to the Luke Skywalker problem or the Shanghai problem. Or maybe now we'll refer to problem number 43. What do you get?
2 answers.
Get 2 answers? Now sometimes you get, the calculator say more answers may exist, blah, 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 so you have to be a little careful with that. But according to the book, there is 1 answer at around 0.6 something. So if you got more than 1, you might double check your equation to make sure you didn't. Okay, does that make sense? So that is something new from the standpoint and to be honest, that's what this packet's all about. I mean, we know all of the different elements we need to do all these problems, or Well, some of them we haven't quite learned yet, but in the next week or so we will. So we know all the different elements we need. It's just a matter of putting them together, setting up the problem, and that sort of thing. And I really like that about the AP test. I'm not a big believer in teaching to test. I mean, the MAPS test, I don't know much about it, but not a big, well, okay, never mind. NISA test, I am recording this, so.
You can say it.
NISA test, I mean, whatever. So those things, but the calculus test, the AP Calc test, I think is a really good test. I think these problems, I think the way they write them, I think they do a really good job of making you learn the concepts and understand the concepts. And I think in teaching to it, in going through this review process for our midterm and going through the review process for the final really is good. It's something we don't get to do in most math classes. You know, think about your Algebra 2, stuff like that. You might have a final, you might review for it, but mostly it's learn this, then learn this, then learn this, and 2 weeks later you forget what you did 2 weeks ago, and so forth. So you never have a chance to bring it all together, tie it together, and do that. And we do get to do that in this process. And I really think it's helpful. I think people that have went on from AP Calc and taken it in college, I think it's helped to remember things. It's helped to be successful in later classes because of that. And so this is an example of a situation where we know that we can do slope between 2 points. Now, would you have thought to label this point X, Y? Maybe not the first time you saw it, but I hope the next time you do, right? Or the next time after that, or whatever. And how the derivative is also the slope of that line, and so forth. All right. Anything else? 42. The amount produced is this. T is the hours of production since 8 a.m. At what time is the rate increase? Oh, okay, now here's a trick. The rate of production. What would be the rate of production? This is the production. So A prime is the rate of production. But now they want to know when the rate is increasing most rapidly. A double prime. Right? That's really the inflection point is what it is. When is the rate of production increasing most rapidly? Would be at the inflection point. If they would have said, when is the production increasing most rapidly? You know, then that's just A prime. That would be different. Or when is the production at a max? But when they say the rate increasing, now you're looking at A double prime. Now you get to use your calculator. So I would do the derivative of this on my calculator, although the derivative is not very hard. I mean, derivative of that is 0. Derivative of that inside, that's just 1, so that'd be 48. Minus 12, t minus 3 to the second, that would be the first derivative. Derivative inside is 1. Second derivative would be, bring down to 2, that'd be negative 24. T minus 3 to the first times 1. So there's your second derivative. Where does that equal 0 at t equals 3? So 11. Now, what we didn't do there is really prove that that's an inflection point. If this was a free response question and we had to justify our answer there, it's not enough to just do the second derivative and set it equal to 0. To find the inflection point, we have to show that it changed concavity. So technically, we would need an A double prime thing here. We'd put a 3 on it. We would check numbers on each side. We would come to our A double prime here. We'd put in a 2. That would give me a negative times a negative is positive. And then we would get put a 4 in here. That'd be a positive times a negative. That's negative. There's a change in concavity. So it is an inflection point. And so there we go. Okay. So but for a multiple choice, on the actual test, you would not have to justify that since none is not one of the choices. That is going to be. All right, we got time for one more. Yeah. All right, I'll give you a hint on 45. 45 is one that I debated on whether I would circle it or not. Is this one we should know how to do? We can do it, but when I probably wouldn't put it on the midterm because it'll be easier to do later when we do integrals and area, because you can see with the squares it might have something to do with area, and so it'll actually be easier to do when we get into those. But we could do it here. It's really a speed limit law. They tell you that f of 2 is 10, which is like giving you a starting point. This is the f prime graph. They tell you f of 2 is 10, so what's the max value of f? Okay, well, so what you can see here is f prime is positive all the way to 6, so that tells you f is what? Increasing. So it's going to increase all the time. So the max is really going to be here at 6, right? So how much is that going to be? Well, think speed limit law. Like right here at 2. Look at the y values. Here's my hint. The y values of this graph are what you want to look at. Because this y value here is like 16. So that means right here the f graph is going over 1 and up 16. Now, at 3, it's up here at about 20 something. So it's going over 1 and up 20. So between 2 and 3, maybe take an average of that. So look at these y values. That tells you about how fast it's going up, kind of like a speed limit law. And just do that all the way along to 6 and kind of get an estimate of how far it goes. Now, the problem is it's a pretty rough estimate, and some of these answers are fairly close together. It might be hard to get the exact one, but try that and see what you come up with, and then we can talk about it again at a later time. But that's how I would start to go about that. Okay? All right. You can put those aside then, and we'll come back to that again, but then we'll be moving on to the free response ones as well, and then getting another packet here pretty soon too. So we may not spend a lot more time on those multiple choice ones. So if you have a bunch of other questions, again, get into this or get with somebody or come see me too for some help on those. Okay, so let's talk about what it is we have to do today, which is section 4.3. All right, 4.3 is about optimization problems. And optimization problems are really global max-min problems. So when we were doing global max-min, what was our strategy? List of candidates, right? And the candidates were what? Endpoints. Well, local max-min, which we looked where? Where derivative is 0, and then the one we just talked about but didn't really have to work any is where the derivative is undefined, right? Like you could have a sharp point to be a local max, right? So there's 3 places. Really, we'll talk about 3 places we have to look. There's endpoints, there's where the derivative is 0, and where the derivative is undefined. Those are our candidates. And then we plug those back into the original function rank, that kind of thing. So we've done some of global max-min problems already, and we're going to review that here. Now remember the names. Derivative 0 is called what? Where the derivative is 0. Yeah, but I mean, what was a fancier title? What's it called at a point where the derivative is 0? Stationary point. What about where the derivative is 0 or undefined? Critical point. Critical point. So critical point means the derivative is 0 or undefined. Stationary point means just derivative 0. So you could say there's 2 places where endpoints and critical points. Right? Endpoints and critical points. The critical points is made up of 2, where the derivative is 0 or where the derivative is undefined. Okay, so anyway, just the terminology. But that's where we got to look. Those are our candidates. All right? And then we have the issue of what happens if you only have one candidate. You know, if you don't have endpoints and you only have one candidate. You can't really do a list of candidates because there's nothing to compare it to. So what do you do in those situations? We'll talk about that. All right? So we've kind of already done that scenario. Where this is going to get tough is the story problems. Because we're going to do real life kinds of problems. Well, real life kind of problems. These are the ones that we talked about back in 3rd day of class, whatever. We did Appendix G. Remember the snowmobile guy stuck in the snow? He's got to get to the gas station. Should he walk straight in the snow? Or which way should he go to get there in the minimum amount of time, right? That kind of stuff. Because that's a minimum. We're finding the minimum time. Or we'll do profit problems. We want to find the max profit. Or we'll find we're going to do an example here in a minute of volume. We're going to make a box, and we want to know how do we make it so we can get the maximum volume, right? These are what optimization problems are, max or min. Optimum just depends what we're looking for. If it's profit, max is the optimum. If it's cost, minimum would be the optimum, right? And so sometimes we just use the term optimization. Okay, so getting those problems set up is where we have some difficulty sometimes. Okay, so let's go through this kind of in a, progressive way here. All right, so the first problem we want to do is going to be this function right here. We'll start off with one like we have already done this year. Now, these will mostly be calculator problems. So you can get your calculators out and ready to go. And we'll talk about some things you can do on your calculators to help you. Wait a minute, that's supposed to be x cubed. And then, there we go. And this is going to be on the interval -1 to 2. All right, so the problem here is find the global max and min value of this function on the closed interval -1 to 2. Now in your book, as we get started on this, in your book at the bottom of page 234, they have something called the extreme value theorem, which we're going to talk about later on. But it says if f is continuous on a closed interval, like this one, then f will have both a global max and min value. It just means that if it's a nice smooth curve and it's got a starting point and a stopping point, there has to be a high spot and there has to be a low spot. I mean, that makes sense, right? So, if you got a nice smooth curve and there's a starting point and a stopping point, then there's got to be a high spot and a low spot. A continuous function on a closed interval can only assume its maximum in values at critical points or endpoints. That's another thing to say. That's what we just talked about. That's our list of candidates. It's got to be at those places. That can't be anywhere else. Okay, so we're going to use those two facts to help us out here. Okay, so here we go. List of candidates, right? Doesn't matter what order I write this stuff down. I know I'm going to need f of -1, and I know I'm going to need f of 2, right? Now, I could have wrote that down later. I don't need to write it down right now. But remember, we always plug those back into the original. Okay, what else do we need besides endpoints? So we do the derivative, 6x squared minus 4x cubed, set it equals 0. Now, even if you're using your calculator, this would all need to be on your paper. Right? Now, at this point, it would be okay for you to get on your calculator and do a solve with this if you would like to, right? And go ahead if you want to. Others may prefer to just work this out by hand. We cannot factor out a 3, so maybe I should be using my calculator instead. If I'm going to do something stupid like that. I can factor out a 2, though. I can factor out a 2x squared, be left with 3 minus 2x. Right? So this part wouldn't have to be on your paper if you were using your calculator to solve. Okay? And so this would be x is 0 or x is... This is where you might want to use a calculator because I was about to say 2/3, but it's actually 3/2, right? So if you solve each one of those, it's that right there. 0 and 3/2. So these two parts here in red might not be on your paper. No, this one line, I guess, is all. This one line right here would not be on your paper if you had just solved in your calculator. You just went to there. Okay, that's just fun. But I think a lot of these will be where we can use our calculator. All right, so now we need to do f of 0. And we need to do f of 1.5. Probably okay to use a decimal here because we're wanting to compare these values, so I'd probably rather have decimals and fractions anyway. And we have to plug those where? Into the original. Now, somebody in the other class, I've kind of forgotten about this, but somebody in the other class brought this up. They asked for a reminder of how to put this into our calculator with those curly brackets. Remember that? Mm-hmm. And so I thought that's a good thing to do. So let's do that. remember, to do that, it is not a solve. You're not solving when you plug numbers into a function. Okay? You're not solving, so don't put solve. You just type the equation. So it's 1, was it a plus? 2x cubed. Don't forget the right arrow there to get out of the power. Minus x to the 4th. And then right arrow. And then what? Vertical line, meaning such that. And then, and don't forget this part where, whoops, I just typed an F. X equals, you have to put that, and then the curly bracket, which you get from the right parenthesis button. And then you can type in your -1, comma, 0, comma, 1.5, oops, 5, comma, and 2. And then hit enter, and you can get all 4 of those values at once. Okay? Not, you know, I don't care. It's just, you know, how you plug them in and what you do. But that's just one way to do it. Now, somebody else brought this up, which I thought was good to share. You can type the word define. When we get one of these problems where you know you're going to be working with a function at various times throughout the problem, you can go here to Menu, Action, and Define, and I could type define f parentheses x equals, and then 1 plus 2x to the 3rd. I don't know if this is faster, but this is just something this person was doing, which I thought was interesting. X to the 4th. Hit enter. And now I could have just done, so for example, let's say I wanted to do the derivative now. So then I could have come in here to my derivative. Now I realize this derivative is pretty easy to do, so you might not have had to worry about it, but let me come into the derivative here. I'll put an X. That is okay, thank you. And now right here, all I keeps disappearing.
Does this happen in the other class too?
Well, actually, in the other class, I kind of cheated and I sat down at the desk one time ago. Okay, so here we go. So notice it's bold-faced because it knows it's been defined, and so I could just, oops, I could just do the derivative right there, and then if I had to do a solve, you know, I can grab that. That was bad. Oh, what did I do? I just deleted it, didn't I? Okay, yeah, this is really working well. This is much, much faster. Yeah, this is great. Okay, do my derivative. Solve, arrow up here. Grab that, equals 0, comma, x. There's my 2 answers. Now I want to plug those in. Now I can just do f of x, my vertical bar. You know, I don't have to type the whole thing out anymore. And then I can do the x equals, and then the curly bracket. And then the -1, comma, 0, comma, 1.5, comma, 2. You know, and so forth and so on. So just some things that your calculator can do that you might not have thought of. Because we are going to be doing that. We're going to find a function we're trying to maximize or minimize. You can define that in your calculator as something and go from there. Now, I've also graphed this thing just for the heck of it. If you're using your calculator, you can do that. Now, it's not good enough for any of your justification, so you still need to have all this on your paper. Now, what did we have here? We had a 1 here. We had a 1 here. We had, what was it, what was f of 2 on this one? Or no, f of 1.5 was 2.66 what? 8, okay. What was f of 2? Oh. And this was -2. Okay. So our max, so there clearly our max is at, and then the way we did this, remember, is we would just write max, because usually they just want the max value, but you answer the question that was asked, and here's your minimum value right here, okay? And there's your max, there's your min, your lowest value, your biggest value. So we've done that. right? We've done that. And if you look at the graph here, you can see, sure enough, the minimum's back here, looks like it's about -2, and then the maximum's here at 1.5, and it's about, it's 2.668 or whatever. And so there it is. And there's the max and the min of that particular function. So if you want to graph it, you can, but you certainly don't have to. Because you do need to do this justification. It's certainly not good enough that if I say find the max of this function, that you just graph it, draw a picture, say here it is, and trace to it, for example, or whatever. That's never good enough. This stuff has to be there. Do your derivative, show your list of candidates, all that stuff. But it can be a way to check. Now, let's talk about number line. Why don't we use a number line for global max min? Yeah, but more than that.
You know what the local max is, but you don't know if one's bigger than the other one.
There's no comparison. We know when the graph goes up and down, but we don't know anything about the endpoints from a number line, and we don't know for sure. Now, a number line can be helpful, and sometimes it can be enough. Now, in this particular problem, it would have looked like this. If we would have done a number line on this, 0, 1.5, okay, so I'd have put a 1 here, put a 2 here, put a -1 here. If I go back and put those into here, okay, if I put a -1 in here, that's positive. -1 in here, that's positive. If I put a 1 in here, that's positive. Put a 1 in here, that's positive. Put a 2 in here, that's positive. Put a 2 in here, that's negative. Okay, this would have been enough to tell me the global max, right? Because this tells me, all right, this function is always increasing until 1.5. Notice the word always. And we're going to talk about that here more a little bit in the next problem, because this is acceptable on the AP test in a number line for a global max min. So there are times where a global max min could be used. This function's always increasing to 1.5 and then always decreasing after. We know it doesn't change anymore because these are the only critical points. So always increasing before and always increasing after tells you that has to be the absolute max. But it doesn't tell you the min. Because if the function, think about it, if the function's always going up and then coming down, what you don't know is how far down does it come. Does it stop right there? Then this would be the min. Or does it go down to here? Then this would be the min, right? You don't know. So you need that comparison. That's why list of candidates is the first thing I would go to, because that works most of the time. But a number line could be used as a possibility. All right, let's look at the next example here. So let's say we have this function. So that's not anything new really right there. Oh, you know what is new though? We said where the derivative is undefined. We have to discuss where the derivative is undefined. In a lot of these problems, here's all you're right. F prime, never undefined. We have to at least acknowledge that we have checked all the possible candidates. Here, a polynomial, a simple polynomial is never undefined. What kind of functions are undefined when you do what? Divide by a 0, right? If you have an x down at the bottom, and so if you divide by 0, that's no good. Or maybe a negative inside a square root, that kind of thing. But otherwise, things are defined usually. So a lot of the times our f prime's not undefined, but every once in a while we'll run into one and we got to remember to use it. Okay, so I'm going to keep reminding you, hey, write this down, write this down. Okay, here's f prime is 0, f prime's never undefined, and here's my endpoints. I checked all my candidates. All right, next one. F of x is equal to x minus x cubed minus 3x to the 4th. No endpoints. So the answer, or excuse me, the question on this problem is find any. So we're not guaranteed to have a global max min. Think of a parabola. If you don't have any endpoints, is there a max on a parabola? Is there a high spot on a parabola? No, there's no global max on a parabola. If you don't have endpoints, you're not guaranteed to have a high and a low spot. Okay, so this problem would say find any global max or global min for this function. Okay, so where do we start? Do the derivative. So here we go. So let's do the derivative. We'll look up here. Like you said, we set it equal to 0. You do the derivative, or let the calculator do the derivative. But as far as I'm concerned, when we get into this, there are going to be some functions we get to that are pretty ugly. And I'll expect you to just do the derivative right on your calculator. Okay? I mean, simple one like this, sure. Do it. without the calculator. But, you know, I guess you could make a dumb mistake doing a derivative, but you could make a dumb mistake typing it into your calculator too. So, I mean, you know, you just don't do dumb mistakes. All right.
Don't be dumb.
Easy to say.
Gosh.
All right. Now, this is not one we could solve. We can't factor out an x or FOIL or anything. So this one we literally have to solve on our calculator. So go ahead and do that. Go ahead and get this one and do a solve on your calculator here. And let's find our stationary point. Those guys walking?
I don't know.
Great.
I'm not sure.
Whatever they eat. All right, so somebody got something? 0.367. Now you want to keep more decimal places than that because if we have to plug this back into our original, which we may have to do, then we'll want to plug in more than 3 decimal places because we'll want our final answer to be accurate. But it's okay to write on my paper 0.367. So there's my stationary point where the derivative is 0. F prime is never undefined, so I'm going to write that down here. So that is not something we have to concern ourselves with because it's just a straight polynomial, so we don't have any issues there. And there are no endpoints per se. Okay? I guess you could say negative infinity and infinity are endpoints. Okay? So let me approach this now from 2 directions then. All right? There would be 2 different ways we could now justify whether we have a max or a min and how we would work this. Okay? So I would do this. Well, does anybody have any ideas right now just looking at this? Did you add those miles now onto your...
You did mine as well.
Were you walking?
Yeah.
Okay. All right, so is anybody just... Where were you stranded?
Well, at my house, but we got.
Oh my goodness, well that is a
we
lot.
had to- Yeah, we had to jump the car. So just like, yeah.
All right, so how about this function right here? We're doing a global max min problem. So for this particular function right here, just thinking about what that function looks like. Do you have a sense of whether this is a max, going to be a max or a min? Because what's this function going to look like?
Both of the tails will go to negative infinity.
Won't they go down? I mean, it's an even powered function. It's got a negative coefficient on it. So the tails are going to be going down. So this has to be a max. Okay? And you could actually use that as your justification. Now, we're going to get into a lot of functions where you're not going to know what it looks like. And now, even though you have the calculator, but again, it's not good enough. Now, this is kind of interesting. Here I tell you, you can't look at a graph and say this is the max and this is the min. You have to use a calculus justification. And here on this one, I'm telling you, but you still have to find the stationary points and all that, right? You can't just look at it and say, oh, it's here. But once you find the stationary point in that, then if you want to use that graph to justify max or min, you could. But for the most part, that would be something you could use. Now, to be honest, that would be more on a no calculator, I think, where you could write that out. But those happen so rarely, I don't want to make a big deal about that. But somebody asked about it in the other class, so I thought, well, in case you're thinking about that. Okay, so here's the 2 ways I would do this. One way is if you only have one candidate, you might think, well, I'm not going to do a list of candidates because we have none to compare to, so it doesn't make any sense to do a list. So if we only have one candidate, let's do a number line. So that's a legitimate way to do this. So we'll do an F prime number line. We'll put 0.367 on it, and we'll take a number like 0. We'll take a number like 1, and we'll plug that back into the F prime. So we put in 0 and we get 1, which is a positive. And we put in 1 and we get 3 here, we get 12 here. So 1 minus 3 is negative 2. Negative 2 minus 12 is negative 24, definitely a negative. So on the AP test, I remember when I graded AP tests, we had a problem like this on the AP test on the free response that year where there was a max min problem that only had one candidate. And they said if they do a number line, but you have to describe it then. And the key word is always. You can't, in a local max min, you just say, hey, this changes from positive to negative, so f changes from increasing to decreasing, and that's a local max. That's all you have to say. In a global max-min problem, you got to say it is the maximum. So you have to say this. The function is always increasing before 0.367 and always decreasing after. So therefore, this is a global max. And that's the secret, is to use the word always. All right? Because it is the only candidate, the only stationary point, so it isn't going to be changing positive to negative anywhere else. So we can use that as a justification. So if you want to, you can. Now, another possibility is to do list of candidates like this. And some of you are going to prefer this because you're going to want to just remember the one thing, for your list of candidates. If it's a global max-min, do list of candidates. Global max-min, do list of candidates. And I'm fine with that. Because to be honest, even on this one over here, on the number line one, you're still going to have to do about the same amount of work because they probably asked for the max value. So you're still going to have to take the 0.367 and plug it into the original. Right? You're still going to have to because they're going to want the output. So you're still going to have to do that. Okay, so we would do that here, and I don't know, has anybody done it yet? 0.263. Okay, now we have nothing to compare it to, so here's what we could do. Instead of talking about in points, let's talk about in behavior. In other words, let's think of negative infinity, infinity as being our endpoints. Now, as you know, infinity can't be an endpoint, but we could just do this. What's happening to this function as x goes to negative infinity, and what's happening to this function as x goes to infinity? That's one of the reasons we talked all about limits and everything earlier in the chapter. Okay? So let's look at this original f function. Let's do infinity first. So as x gets really big, these lower powers don't matter, do they? So the only one that really matters as x gets really big is this high power. What's happening to that as x gets really big? Going to negative infinity, right? X to the fourth is getting really big, times negative 3, so it would be negative. That's going to negative infinity. Okay, and then put in negative infinity, same thing. The fourth power will make it positive, then times negative 3. So again, it's going to negative infinity. So right there, that is a good enough discussion to show, hey, here's a max, and we don't have a min. There is no min because it goes to negative infinity, but the max is 0.263. Okay? And so a list of candidates can be done with only one candidate. I mean, let's face it, if you only have one candidate, it means you didn't have endpoints. Because if you have endpoints, you got two candidates right there. Okay? So if you only have one candidate, you probably didn't have endpoints, so you can discuss the in behavior. That's a legitimate way. But you can also do a number line. Okay? Say that's the max, but you're still going to have to take the 0.367, plug it in, to get the 0.263. All right, so that is kind of review, but we added in a few little technicalities there, like with one candidate and F prime number, undefined stuff, but mostly it's stuff we've done before with global max-min. All right, so now what about the story problem part of this? What about what's going to get, what are these problems going to look like now in chapter 4, these kind of real life kind of problems? All right, well, here's one right here. This is a document. You don't have to get this out on your calculator because this particular one runs kind of slow. I think I sent it to you at the very beginning of the year. It's called What is Calculus? And at towards the very end of this document, it says calculus can help a manufacturer find the optimum shape to minimize cost. Optimization of functions is extremely beneficial for real-world problems. So optimization type problems, like we said, the guy's stranded in the snow. What's the minimum time that he can get to the service station? Right, that's an optimization problem. So if we go on to this one, we're going to do this problem right here. We've got a sheet of paper, 8.5 by 11. We want to cut squares out of each corner, equal size squares, so that we can fold it up into a box with no top. Okay, open top. What size squares should we cut out so that that box will have the biggest volume possible? That's what we're trying to do. Okay? Well, what are we trying to maximize? Volume. Okay, now, think back to the problems we just did. What were we maximizing in those problems? We were finding the maximum of the f function, right? It was just some unknown function, it didn't stand for anything. We were finding the maximum of the f function. Here we want to find the max volume. So we need a volume function. You're going to hear me say this over and over. The first step in these problems is identify what you're trying to maximize and minimize. Identify what you're maximizing and minimizing. Then that's the function you need to write. The hardest part of these problems is writing the function. Once you get the function written, then it's just like the last two we just did. You guys, and trust me, every year it's like this. Once you get to having the function written, then you know what to do. Right? The calculus stuff is the easiest part of this. It's the algebra stuff that gets us. The setting up the equation. Once we get the equation set up, then we do our list of candidates and away we go. We've got to get the equation up. So that's what we'll be practicing as we go through these different types of problems. And the more of them you do, the better off you'll get. So we are trying to find the max volume. Now, this little picture is kind of a neat way to just see it, what's happening, but it doesn't really help us find it. But here's what's going on. So the white is the little corners we're trying to cut out. And you can see if I cut out that size of corner, I get that box. Now, I've also got a graph of the volume going on right here. So you can see what happens is that as I cut out bigger and bigger corners, my volume goes up. So those boxes are getting bigger and bigger. But at some point, they start getting smaller and smaller. So where is the optimum? Well, it's right in there somewhere. We can see from the graph. So right in there somewhere is the size of square we should cut out to give ourselves the max volume. So how do we find it? That's what we're going to do. So we want to find max volume. We need a volume equation. What's the volume of a box? Length times width times height. Now this is going to happen often. That when you identify what it is you're trying to maximize or minimize, it's going to have more than one variable. So then you have to get it down in terms of one variable. So draw a picture, get some extra information, something. Now in this case, I'm going to draw a picture. So here's our piece of paper. Okay, it's 8.5 by 11. And we're going to cut out these squares to fold it up into a box. Change colors here a little bit. So this is the bottom of our box right here. Now somehow we need to get a variable in here, and this problem kind of takes care of itself. Now you may not think how to do this right away, but what's the unknown that we have here? How big a square is the cutout, right? So let's call that x. Now that has the added benefit of being what dimension? What dimension of the box is that x? Isn't that the height of the box? When we cut out these squares and fold up, let me scribble those out here. So what's happening is this is gone, right? We're cutting that out of there. All right, and we take these pieces and fold them up. This x is our height. So that's the height of the box right there. So what is this length and this width then? Okay, this one right here would be 11 minus 2x. Everybody see that? Because we're cutting x out of this side and x out of this side, and the whole length is 11. So the length, or the width, I guess it doesn't matter which one, is 11 minus 2x. And the other one? 8.5 minus 2x. Very good. And so there we were able to write this now in terms of only one variable. But now you got to imagine, as we get through this over the course of the next few days and week, is to be able to take that situation that I described to you in words and get to this point. Right? Be able to draw yourself a picture, identify a variable, and be able to write an equation for this thing. But once we're here, now it's just what we were doing in the last two problems. What we're trying to do is find the max volume. So we're trying to find the max of this function. So we need a list of candidates. So where do we check? Oh, endpoints. This would be a good time to do endpoints. That's another thing that's a little tricky in these problems. In the problems I've done with you in the past, we've just given you the endpoints. You have to think about them. Now remember, your endpoints are x values, input values. So you have to think to yourself, what's the littlest x could be? And what's the biggest x could be? So, littlest first. What's the littlest x could be? 0. Now some might argue, but wait a minute, if x is 0, you don't even have a box, right? You didn't cut out anything. That's true, but we can use it, right? Because what else could the littlest be? 0.1? No. 0.05? I mean, you know what I mean? It's 0. Does that mean you don't have a box? Sure. Well, that happens a lot in these problems. You're looking for a maximum. The endpoints a lot of times are the minimum. You know, the one you don't want, the other extreme. Okay, and it works that way a lot. So 0, I would say, is what we would put for the littlest x could be. And what's the biggest x could be? 4.25. Very good. Because the bigger you cut x here, these start to come together. Now this side's shorter than this side, so we'd run out of room, we'd run out of paper sooner on this side. So once you get to the middle of this side, 4 1/4 here and 4 1/4 here, you've used up that whole side. So 4 1/4 is the biggest that x could be. So there's your endpoints. All right, so what do we do now? Do the derivative, do our list of candidates. So we're going to do our list of candidates where the endpoints, where the derivative is 0, where the derivative is undefined. Now this is just a cubic function, so again, the derivative is never undefined, so we can write that down. B prime is never undefined, so we take care of that. So that's not an issue. Remember, 3 places we got to check. Endpoints, derivative 0, derivative undefined. Endpoints are taken care of there. Derivative is never undefined, so now we do derivative set equals 0. So do it on your calculator, I would say. I mean, if you want to FOIL that all out, you could. This would be a great one to do on your calculator. Don't forget that this x, some people in the air class, I guess in the air class we wrote it this way. We wrote x parentheses like this. You have to put a dot in there. You have to put a time sign in if you do an x in parentheses. Otherwise it thinks it's a function. Right? It thinks it's x of something. It doesn't understand that. So you can't do x parenthesis. You got to do x times. Just like you can't do x cosine. You got to do x times cosine. Okay? What's a derivative? And then we got to set that equal to 0. Make sure you put equals 0. Okay? So even though you did the derivative on the calculator, you need to write it down. You need to set it equal to 0 and then do a solve. So the calculator gets to do quite a bit of this for us, but we have to write down our results and what we're getting and so forth. What do you get? Okay. Now, what about that second one? Throw it out. Too big. Look at our endpoint. 0 to 4 1/4. So 4.915 is not going to work. Matter of fact, and what you'd have found is when you plug that in, I think you'd have got a negative. And so you just said, right? So if you wouldn't have noticed that and you would have still put it in your list of candidates, it probably would not cost you. Okay? But where it would is if it gave you a viable answer maybe and you used it, and then so you do want to try to catch something like that. All right, so now our list of candidates would be a good way to go because we got our endpoints. All right, so now this would look like V of 0, V of 4 1/4. Although we know both of those don't even make boxes, so they both have a 0 volume. If we put those two numbers in, they both give us 0. Okay, and so that certainly isn't going to be our max. So we feel pretty good about the fact that this one is going to be our max. We plug that in, and you get 66 point something. All right, for your maximum. Now, again, this thing in real life examples, the endpoints get tricky because a lot of the time the endpoints are not really legitimate possibilities, like in this case. The endpoints are a situation where you don't have a box. So some people get bothered by that and don't want to use the endpoints there. And then we could do kind of a number line situation. You could argue that this is a one candidate problem, that the only real candidate is 1.585. And if you then do a number line with that, and you get positive, negative, you could argue that you could say, hey, as you cut out these corners, the volume is always increasing, and then after that is always decreasing, so this has to be the max, and I would be okay with that argument. Okay? If you feel like those are not really legitimate endpoints because they don't make a box, the only one that really does make a box is this one, and use a number line argument, I would be okay with that. All right? I'm also okay if you go ahead and use them in that case. And that happens quite a bit in some of the problems that we do. All right? If you really understand what's happening, you should be okay going either way with that. Now, then you would want to answer the question. When we do our mathematical global max min, it's usually what's the max value. So we want the output. But in this problem, they might have said, how big of squares should you cut out? So what would you answer? Yeah, squares that are 1.585 on a side. That would be your answer. If the question was, what's the biggest volume box you can make? Then it'd be the 66 point whatever. So at that point, you just answer the question the way it's asked. Okay? All right, let's do one more. Now, it's just impossible to cover all the different possibilities. And we'll, as we go along, we'll do more and more, and you'll have your homework problems to try. But as you do them, you'll get more comfortable with the process. So here's the last one we'll try. Two numbers add up to 18. Now, when I say two numbers, I think in this particular problem, we're saying non-negative numbers. Two non-negative numbers. Okay? Isn't that the same as positive? Could be zero, right? Non-negative would equal zero. Okay? Two non-negative numbers add up to 18. Find the proper to use a comma and then follow that with a capital F. Find, in case Mr. Mishu, find the largest product, and my grammar is really bad here. I'm going to have to end this sentence. Two numbers add up to 18. Find the largest product. Oh, here. I can't think of anything else. All right. Find the largest product. Find it. Really, what I should say. Find the two numbers that add up to 18 that have the largest product. That's what we're trying to do. Okay? Non-negative numbers. Now, this is pretty simple, really. Some of you already know what it is. Anybody got to take a shot at it? 9 and 9, right? 9 times 9, because 8 times 10 is 80, 9 times 9 is 81, you go back, 7 times 11 is 77, right? The largest is, and that goes back to the old thing, if you have a fixed perimeter, what shape would maximize the area? If you want to do a rectangle, it's a square, right? The maximum area, and that's really the same thing. Perimeter you add up, so you have a fixed perimeter. This is like having two numbers that are fixed. They have to add up to 18. What's the largest area? Area is length times width. That's product. Okay. The most efficient, if you're going to make a, pasture for your cattle and you want to maximize the area you can enclose with a fixed amount of fence, you make it a square. Well, actually, you make it a circle, but if it's got to have 4 sides, okay, if it's a rectangular shape, then you would make it a square. Okay, And so we already maybe just know that. We could write down a few numbers, we can see a pattern, whatever. But what we're trying to learn here is the process. We're trying to learn the process of finding these maxims. So we're going to go through that process. Okay, so I've already talked about the steps. So the first step is to identify what you're trying to maximize. What is it here? Product. So since we're trying to maximize the product, we need a product equation. P equals, right? If we were doing profit and we want to maximize profit, we need a profit equation. P equals. That's our first place we start. If I'm trying to minimize cost, I need a C equals equation. Last problem, we were maximizing volume. We started with V equals. Okay, in this one, we're maximizing product, so P equals what? Times. Okay, you're jumping ahead of me. That's really good, but I'm going to put y, right? I got two numbers. I don't know what they are, so let's call one x and call one y. Okay? Call one x and call one y. Now, Brenda had a great idea, but I shot her down once again.
Wow.
You shot her down. Yes, but that's exactly right. But she took a couple pieces of information, put it together all at once, and that's really good. But we might not see that. So that's what we write. And just like when I did volume equals length times width times height, we had multiple variables. What we'd like to do is get it in terms of just one variable, right? So there's got to be other information that will let you do that. In this case, it's this right here. So how can I write the fact that two numbers add up to 18? X plus y equals 18. Now, and again, the reason that I shot Brenda down, other than it's just kind of fun, but is that as the problems get a little more difficult, right? Yeah, I've said a lot of that. As the problems get a little more difficult, the equations get a little more difficult, and this is what it'll end up looking like. You'll have one equation here. Like, for example, we'll be looking at a cone, maybe, and we want to maximize the volume of the cone. So that'd be V equals 1/3 pi r squared h. But then we'll have information about the cone, about how its radius and height relate to each other. So we'll be able to set that equation up and then substitute, and that's what we're going to do right now. Okay, so the first step is identify what we're maximizing, which is product, so write a P equals equation. Then see if there's any other information that can help you get it down to one variable. In this case, there is. So now we would just solve one of these, so y would equal 18 minus x. We can now take that and substitute it into this equation. And so in place of y, we have that, right? We now have it in terms of one equation. Now we are at the point we were in our earlier mathematical examples. We now have our function that we're trying to maximize or minimize, in this case maximize. And I'm going to simplify that a little bit. So that's 18x minus x squared. So we now do what? Oh, we haven't talked about endpoints. A lot of times you forget about those till you do your list of candidates, so you end up doing those at the end, okay? So let's do that. Let's pretend we forgot about those. So we do the derivative. We get 18 minus 2x equals 0. Sure enough, x is going to equal 9. So once again, we could argue that this is a one candidate situation, that the endpoints aren't really going to give us anything, because think about what the endpoints are. What's the littlest x can be? X is one of our numbers. If they're non-negative, it's 0. What's the largest it could be? 18. If it's 18, the other one is 0. Well, when you do a product with that, you're always going to get 0. So there's no way that's going to be the max. So again, it's very much like the last problem. So you can do your list of candidates, whereas two of them really are not going to make much of a product. So P of 0 is going to be 0. P of 18, we try it. Put your 18 in here, you're going to get 0. Okay? And then P of 9 is going to be 81. So some of these examples we start with are somewhat trivial in the sense, but it's the process that we're trying to get under control, so that when you get stuck, you at least have something to think about. What am I trying to get next? All right, and then what did it ask? Did it say what are the two numbers? Well, 9 and 9. Okay, If you want to know what is the product, 81. Okay? Now you could do a number line situation here again. If you argue that those aren't really viable candidates, you could put 9 and show that the product is always increasing and then it'll start decreasing, so that's the max. All right, so to sum this up then, and then I'll let you get started on your homework. I've just written down kind of a recipe. I'm not a big believer in just memorizing steps. I think you need to understand the overall process. But I think this is a case where this can be helpful. And so I'll leave this up here. I'll have this up several different times at various days. So if you want to write it today, fine. But when you have a max-min problem, story-type problem, where you're finding a global max-min, the first step is to identify what you're maximizing or minimizing. In our math examples, that was easy. They just told us. They said, here's the function. Find the global max-min. So we didn't even have to do any of the first 3 steps. Right? We just jumped right down to here. Find the critical points, endpoints, list of candidates, answer the question. Okay? But in these story problems, we've got to identify what's being maximized. Profit, you need a P equals equation. Minimizing cost, C equals what? Area, A equals what? Then write, and well, that's what I was just saying, write and label an equation of that quantity. So we need an A equals, a P equals, a V equals equation. That is called your objective function or your primary equation. I'm not too concerned if you know those terms or not, but that's what they're called. That's what you're trying to maximize or minimize. You did a little of this in Algebra 2, I believe. This objective function and linear programming, it was called. Finding the corners and graph these lines and that kind of stuff. But that was all linear kinds of things. Third step, get the equation in terms of a single variable using other information. Those are your secondary equations or your constraints, is what those are called. So your secondary information. So it helps you get it in terms of one variable, which we did on the last couple problems. So we got it just in terms of an x. And then what, and that, to be honest, guys, that's what's going to be the hardest part, is those first 3 steps. Okay? Getting the things set up. Because once we have that set up, I think we're in pretty good shape there. Find the critical points. See where the derivative is 0. See where the derivative is undefined. Identify your endpoints or your end behavior, like we talked about as x goes to infinity or whatever. Use your list of candidates or a number line for your justification. And then answer the question that they ask, and don't forget units if they're appropriate for that question. Okay? All right, because so often people ask me on these, well, I don't even know where to start. Well, you start with step 1. What are you trying to maximize? You find the max area, you find a max distance. If you're finding max distance or minimum distance, then it's D equals, and you got to write a distance equation or something. Maybe that's rate times time. Distance equals rate times time. Maybe it's Pythagorean theorem, or maybe, whatever, distance formula. But you've got to write an equation. It might have more than one variable, so then you find other information to get that out of it. All right. The homework is only 5 questions, but they don't really have multiple parts. I think one of them might. I think, now we're on section 4.3. I think 22 has a couple of different parts, but actually I think they're just leading you through the steps of the problem, so it's really not multiple parts. But otherwise, I think the other ones are just one problem. But they're kind of tricky. Again, can you get them set up? And so just don't be too quick to give up. The difficult part is if you can't get the equation set up, you can't really do the rest of it. You can't. You know what I mean? So anyway, get together. Story problem party on Sunday. Somebody's house, whatever.
Mr. Clark. Yeah, and behavior in step 5. That was when the tails went down.
Yeah, like if you don't have, they don't give you specific endpoints, and so you're just kind of using infinity. You know what I mean? That's kind of what I meant. What's happening with the units. So anyways, 4.3 day one, 4.3 day one is the line we're on. Answer books up here if you need to refer to it.
Yes, you have answer for
For the packet.
Okay, I have a question on logistics.
What's that?
I have a question on logistics.
Yes.
If it said to like find the two numbers that have an 18, if it's
Mhm.
different numbers or not, how would you say?
If they had to be different?
Yeah.
Oh.
Where are you showing it?
Um,
Well.
I don't think you would have that, to be honest. In that, there wouldn't be. I mean, because it's gotta be 9 and 9, so 8.9 and 9.1. But you see what I mean? If you got one number just a little less than 9 and one a little bigger than 9, you'd have a good sized product, but it wouldn't be as big as 9 times 9. So you'd have to keep getting closer to there. You know what I mean? So I can't think of any example where that would be, where it wouldn't just happen automatically. You know, where you have to do anything special in setting it up. It just came out that way. So. Yeah.
May I go yes?
Yes, you may, Brenna. I will not shoot you down in asking you to go to the restroom. What's that? Is it? Yeah, I know.
Oh.
I saw it on the desk and I was like, wait.
Wait, is that my reveal?
Let's all just get up and get it done.
Jeez, Christmas.
Everyone just leave me.
I'm just being frozen.